Let's now rewind a little bit to your early years, childhood in the Netherlands, and how you got started as an astronomer. Formative influences in your life. Where were you born?
I was born in Groningen.
And what kind of place is that?
Northern part of Holland. It always feels neglected by The Hague, where the center of Holland is, as it were. Amsterdam, The Hague, Rotterdam. But I like Groningen. I don't speak the dialect, but I can't understand a word of the dialect.
Even though you grew up there?
Yeah. When I cross over to Friesland, halfway to Leeuwarden, there is Frisian, which is a real language, not a dialect.
Mm-hmm.
Can't understand it at all.
Is that because you once could do these things, but you just forgot because you've left the place?
I know only one word in Frisian. Father is heid.
Okay.
So it's but anyhow.
Your family was not a science family.
No. My father was a government accountant, and we lived in Groningen happily. During the war years, it was very difficult times. There were great uncertainty because Holland was occupied by the Nazis from 1940 to 45, and there was always great uncertainty what would happen next.
I make it that you were roughly 11 to 16 in those years.
Yeah, correct. Yeah.
Mm-hmm. So very formative years.
Yes. I was lucky in the sense that I was not 18, because the Germans dictated that people of 18 and older had to work in Germany,
mm-hmm.
simply.
When did you choose the course of astronomy in university?
I was an amateur for a long time in Groningen. And in retrospect, I realized that it was easy in the city to do observations out of an upper floor window with a small telescope, because for those years, 1940 to 45, there was a blackout for 5 solid years, and that, I mean, in the current day and age, with all the lights on everywhere, I mean, many young people will not hardly know. The only thing you see is Jupiter in the sky and the moon. So also I had an uncle who did observations of occultations of stars, by which their positions can be more accurately determined and so on. Then I remember that in Holland we had these conferences in the summer where all the astronomers in the country come together and spend somewhere in the middle of the country, in the Veluwe, north of Arnhem, and all the professors, everybody is there in astronomy, and that's very nice.
Very nice.
I met and experienced Minnaert from Utrecht, who was a famous expositor of astronomy. He did a fantastic job, and so on.
How old were you then, and why were you going to these things?
Because every graduate student in astronomy and every astronomer did it.
I see.
Simple. And then at one of these conferences, it so happened that Oort had already apparently noticed me, because he invited me for graduate study to come to Leiden.
Well, tell us now about your relationship with Oort.
Yes, Jan Oort, who is of course over the world mostly known for the Oort cloud of comets, but as an astronomer in the late 1920s, he and Lindblad of Stockholm, Sweden, discovered that the rotation of the galaxy, and that was immensely important. Jan Oort at that time came up with a little model of the distribution of mass in the galaxy that would do it, but it was a very rough model with steps in it, and I, in 1959, published a model in the Kuiper series of stars and
stellar systems?
Yeah,
Yeah.
stellar system. And published it there, and did a job where I had a continuous change of the density, which was much more realistic. Unfortunately, I used a B magnitude of Oort's that was totally unrealistic.
The B constant. Is that what you mean?
B constant, yes.
Yes.
I used -10, and it really should be minus 15.
-15,
it
yeah.
simply was not realized at the time. And I remember that Jim Gunn was one of the first ones who I think pointed out that we were on the wrong track.
Well, we're a little bit ahead of the story, I think. So it's the early 50s, you're showing up as a grad student at Leiden.
Yeah.
You come to Oort's attention.
Yeah.
And there's a golden opportunity there, observation-wise, in radio astronomy. And why is that? What had the Dutch just done during the preceding years?
During the war, Henk van der Hulst, who was a professor at Leiden, he was underwater in hiding during the war because the Germans, as I mentioned, men over 18 had to be transported to Germany to work for the German effort. So Henk van der Hulst predicted that the spin flip of neutral hydrogen should be observable, even though it's I believe I don't know whether it's a legal term, but it may even be very forbidden.
Very forbidden.
But,
but there's a lot of hydrogen.
There's a lot of hydrogen,
Right.
especially in the plane of the galaxy, where you look through light years.
Actually, it's great that it's forbidden, because if it weren't, we
Exactly.
couldn't see very far.
No, you would, it would stop here.
Yeah.
And there are these pictures of that colloquium that Henk gave in the collegezaal, where the classes are given at Leiden at the observatory, while he was really in hiding. And there you see these people all beautifully dressed, but middle of the war. So Jan Oort went to the Science Foundation in Holland and got money to detect the line.
And as I understand it, that was partly your job. Later. Later.
Later on.
And the survey that you got involved in used a leftover German radio telescope,
Correct.
which had to be refurbished. And
correct.
So tell us what this German radio telescope was actually doing. Was it mapping?
No, it was receiving radio radiation, but it did not have motors. It had a altizimuth mount.
And so how did you actually make it point and take data?
You got tables from the people who worked in the Rekenkamer at Leiden, which is the computing room, where you have man who actually do all the computing, who for every 5 minutes gave the position in horizontal coordinates, what I had to do.
And then manually the telescope got moved?
Yeah, so I would do it, then I would do like this and do it like that. And
it must have been very wearing.
Wearing.
Yes.
And also very cold. Once I almost fell off the whole structure when it was icy. And I slipped and could have been killed. Wouldn't be sitting here. Anyhow, and the line was discovered first by Ewing.
Harvard. Yeah.
And then I think at Kootwijk, which was where the dish was, and then in Australia. So everybody got on board, and it was up to, and the first maps soon came out, which showed structure. To call it spiral structure was perhaps somewhat of an overstatement.
So you actually got sort of a plum assignment, I think. I'm now reaching back to my graduate student training days, and I seem to recall that the hydrogen inside the solar circle is more valuable
was my responsibility
than the hydrogen outside the solar circle. You got the hydrogen inside the solar circle.
Yes.
And that enabled you to measure a rotation curve.
All the way out to the solar circle.
To the solar circle.
That's right.
And am I correct? That was your thesis study, is that right?
No.
No, that wasn't?
My thesis was a mass model of the galaxy.
Based on those measurements.
Yes.
I see.
Yes,
okay.
Yes.
Okay, so now what we're doing here is we're laying the foundation for what is actually your most cited paper, which is called the Schmidt Law.
Oh. Yes.
Which you published in 1959, and it's known today as a rule that relates surface density of gas to the amount of star formation. So this is a leading question. It seems to me that you, as a result of your thesis work and collaboration, had two sets of data that were brand new in the world.
Yeah.
One was a mass model for the galaxy, mostly stars.
Yeah.
And then from the hydrogen mapping, a map of the gas surface density in the galaxy.
That's right.
And your paper on the Schmidt Law put that together in a very interesting way. So what were you doing in this paper? How did the idea come to you?
I think Sidney Vandenberg before I published the paper, wrote a short note saying that with the rate of star formation that you can derive from all these data, that the gas will be depleted in a relatively short time, somewhere between 10 to the 8 and 10 to the 9 years.
Was that shocking?
It was not the case.
Not true.
It was not true. It was what he forgot to take into account is that when the stars, say above 2 or 3 solar mass, go off the main sequence, that they shed their mass, eventually end up as white dwarf, and therefore a large fraction of the original luminosity function at formation is returned and recycled.
Yes. So you were the first to take that backflow into account.
That's right.
Yes.
And nobody had done that.
Mm-hmm. As I understand it, that changed the results by some amount, but not by many factors.
Yes, but what it essentially also predicted was how the metal abundance should change. And while the prediction was there, it turned out never to be easy to actually get that out of the data, independent as a check on the model.
So you put this new data set together and
Yeah.
derived a law for star formation
That's right.
that said that the star formation rate goes as the square of the gas surface density.
I made it a square at the time. Yeah, it landed eventually at 1.35.
Based on later work by?
Yeah, where on galaxies like we discussed, where Kennicott, I think that 1.35 is pretty general.
So I'd just like to emphasize, in going back and reading that paper, which I did for this interview, that it really was, I think, the first paper in astronomy to try to make a global evolutionary model for a galaxy.
Correct.
Right?
Correct, yeah.
We start with some gas.
Or at least for the solar neighborhood.
Well, no, but you used data over a wide range of radii, and that was important to your deriving
Yes.
the exponent of 2,
Yes.
to observe that the mass profile in stars is a lot steeper than the mass profile in
Precisely.
gas.
Exactly.
And in order to reconcile those, you needed
That
this
came out very naturally.
very, very beautiful
Yeah.
logic, I think. Right.